Japan and Europe are positioning themselves as world leaders on magnetic fusion research.
Japan has just created something mind-blowing. A machine so powerful it can heat things up to 200 million degrees Celsius, and it has called it the JT60SA. It is basically a mini sun, and this fusion reactor is decked out with a super fancy magnet system featuring 18 massive coils and a central solenoid, all kept cool with liquid helium to handle the extreme heat. However, this weapon, if not handled carefully, could cause a massive catastrophe. So, if something went horribly wrong, could we really handle the fallout of messing with such intense forces?
Over the period 2021 to 2027, Europe will invest around 6 billion euros in fusion development.
Let's dive into the potential dangers of harnessing this incredible power. Fusion energy. Fusion energy is like the holy grail of power sources, virtually limitless and squeaky clean. Unlike its cousin, nuclear fission, which works by splitting atomic nuclei, think of it as breaking things apart, fusion mimics the sun's mojo by combining atoms to unleash incredible amounts of energy. The magic happens inside devices called tokamaks, which are basically experimental reactors that look like something out of a sci-fi movie. These high-tech gadgets are designed to create and study plasma so hot it makes the sun look like an ice cube. Because of the possibilities that this process promises, many scientists from all over the globe are joining forces, each contributing their piece to this gigantic fusion puzzle. There's the colossal ITER project in France, which is like the fusion world's rock star, and then there are smaller, super-focused experiments popping up everywhere from the US to China and Europe. Researchers are burning the midnight oil, coming up with innovative ways to turn this futuristic dream into reality. But out of all these efforts, the JT60SA in Japan stands out as the coolest kid on the block. Why is JT60SA so special, you ask? Well, it's pushing the boundaries in ways that make even the most seasoned scientists raise an eyebrow. It's like the fusion equivalent of having a tricked-out turbocharged sports car in a race full of standard sedans. While all the other projects are fascinating and essential in their own right, JT60SA is where things get really interesting, promising exciting breakthroughs that could change the game entirely. The JT60SA's fusion frontier. In a surprise move just a day after the official opening of COP28, where countries gathered to discuss phasing out or reducing fossil fuels, Europe and Japan chose the perfect moment to unveil JT60SA. This cutting-edge experimental device, the most powerful of its kind to date, stands as a landmark achievement for their policy and scientific communities, research organizations, and industry. At a ceremony held on Friday, December 1st, 2023, the European Commissioner for Energy, Kadri Simpson, alongside Japan's Minister for Education, Culture, Sports, Science and Technology, Masahito Moriyama, and Japan's Minister of State for Science and Technology Policy, Sanae Takaichi, were joined by senior politicians, industry representatives, and the research community to inaugurate the JT60SA facility. From the control room, they witnessed a plasma operation, marking a significant milestone in the project's timeline. JT60SA is the product of the Broader Approach Agreement, a scientific collaboration between the European Union and Japan aimed at advancing fusion research through various projects. Construction began in 2007 and was completed in 2020 with the end of assembly. Since then, a series of technical improvements have been made, leading to the first plasma operations towards the end of 2023. The total cost of the project for the construction phase is estimated to be around 560 million euros, shared between Europe and Japan. This project exemplifies science diplomacy, praised for its collaborative spirit, efficient management, and exemplary execution. The decision to unveil JT60SA during COP28 sends a strong message about the future of energy. As the world grapples with the challenges of climate change and the need for sustainable energy solutions, fusion energy offers a promising alternative. By demonstrating their commitment to fusion, Europe and Japan are positioning themselves as leaders in the transition to cleaner energy sources. This powerhouse is part of Eurofusion, a collaboration that unites around 170 laboratories and industrial partners from 29 countries. It's like a big, happy family of scientists and engineers, all pooling their hardware, expertise, and enthusiasm into making JT60SA a success. Eurofusion has a consortium of 31 European laboratories, and it has made significant contributions in terms of personnel and equipment. Meanwhile, Japan's National Institutes for Quantum Science and Technology, QST, based in Naka, played a crucial role by providing essential resources and expertise. This partnership between research institutions and industry has proven to be mutually beneficial. By working together, these organizations have successfully developed the components necessary for the JT60SA reactor, demonstrating the power of collaboration in driving scientific and technological advancement. So what exactly makes the JT60SA special? Well, for one, it uses the latest plasma control technologies to keep everything running smoothly. Picture a symphony where every instrument needs to be in perfect harmony. That's what JT60SA does with its advanced heating and current driving systems. These systems work alongside various control tools, such as magnetic coils and extra heating mechanisms, to fine-tune the plasma's shape and stability. This precise control is crucial because if the plasma goes haywire, it could spell disaster. So JT60SA's tech ensures the plasma stays just right, making fusion energy generation possible. That's not all. JT60SA isn't just about solving today's fusion challenges, it's also a launchpad for future innovations. This tokamak is a playground for long-term research, not just a one-hit wonder. It aims to pioneer new ways to control plasma, the super-hot charged gas essential for fusion. By experimenting with different methods, JT60SA hopes to make reactors more efficient and reliable, which is a big deal for powering our future. The JT60SA project isn't just about pushing its own research forward, it plays a pivotal role in the global quest for fusion energy. The breakthroughs achieved here are shared with the ITER project, another giant in the fusion world to tackle challenges and refine processes. This teamwork speeds up the progress of fusion science, bringing us closer to the day when fusion power can be part of our everyday lives. By honing these technologies, JT60SA is building the groundwork for a future powered by cleaner, sustainable energy sources. Advancing fusion research. The JT60SA project is shaking up the world of nuclear fusion, constantly evolving to keep pace with new discoveries from ITER. Initially, its primary goal was to support ITER, but JT60SA is now setting its sights on what future fusion reactors will require. Its ambitions have expanded to include enhancing steady-state operations and exploring new plasma scenarios, those tricky conditions we expect in future fusion power plants like DEMO. This project is all about international collaboration, particularly between Europe and Japan. Such cooperation is vital, not just to overcome the technical and logistical hurdles of this complex endeavor, but also to cultivate a robust team of skilled researchers and engineers. This growing community is essential for maintaining and expanding the knowledge base required for future fusion projects. Let's take a closer look at how JT60SA is propelling us toward a brighter future. JT60SA is more than just a research facility, it's a beacon of what future energy could look like. Employing the latest superconducting magnet technology and state-of-the-art plasma control systems, it sets a high bar for future projects. This facility demonstrates the immense potential of fusion energy to become a sustainable, limitless power source. But the journey doesn't end here. As JT60SA continues to advance, it will vastly improve our understanding of plasma physics and help transform fusion energy from a theoretical possibility into a practical reality. This represents a critical step towards a revolutionary power solution that could forever change the way we generate energy. In essence, the JT60SA project is a cornerstone in the global effort to harness fusion energy. By sharing its findings with ITER and contributing to international research, it accelerates the development of fusion technology. The JT60SA is designed to harness the power of the sun by mimicking its energy-producing process. At its core is a donut-shaped chamber where an extremely hot, charged gas called plasma is contained. Powerful magnets keep this super-hot gas under control. JT60SA is a groundbreaking achievement and the world's largest, most advanced fusion reactor. It's a crucial part of the global effort to develop fusion energy, as represented by the International Thermonuclear Experimental Reactor (ITER) project in France. By studying the behavior of plasma in JT60SA, scientists can gain valuable insights into the complex science of fusion. A major milestone was reached on October 26, 2023, when JT60SA successfully created its first plasma after nearly 15 years of development. This is a huge step forward and confirms that the reactor is working as intended. Project manager Sam Davis and the European Union's Fusion for Energy organization, working closely with Japan's National Institutes for Quantum Science and Technology, are thrilled with the results. So, what's the science behind this energy, the science behind the power? The process at the heart of JT60SA is called nuclear fusion. This involves combining two lightweight atomic nuclei to form a heavier one, releasing a tremendous amount of energy in the process. To achieve this, the reactor creates plasma, a superheated state of matter. Successfully controlling this process is a monumental challenge, but it holds the promise of virtually limitless clean energy. While creating the first plasma is a significant accomplishment, scientists still face hurdles in managing and sustaining this powerful reaction. The journey to harnessing fusion energy is far from over, but the progress made with JT60SA brings us closer to a future powered by the same energy that fuels the sun. Plasma is a unique form of matter that behaves differently from solids, liquids, or gases. It's often referred to as the fourth state of matter. Unlike ordinary matter, plasma is composed of highly energized particles, ions, atoms that have lost or gained electrons, and free electrons. This electrified mix is what gives plasma its distinctive properties. Imagine a gas heated to extremely high temperatures. As the temperature rises, the gas molecules collide with increasing violence. Eventually, the collisions become so forceful that electrons are stripped away from the atoms, creating a soup of charged particles. This is plasma. Our sun is a colossal ball of plasma. At its core, temperatures reach millions of degrees Celsius. Under these extreme conditions, atomic nuclei, primarily hydrogen, move at incredible speeds. When these nuclei collide with enough force, they fuse together to form helium, releasing enormous amounts of energy in the process. This is nuclear fusion, the same reaction scientists are trying to replicate on Earth, the quest for earthly fusion. The potential of harnessing fusion energy is immense. It promises a virtually inexhaustible, clean, and safe energy source. Unlike traditional nuclear power plants that rely on fission, splitting atoms, fusion involves combining atoms, producing far less radioactive waste. Scientists have been chasing the dream of fusion power for decades. To achieve fusion on Earth, we need to recreate the extreme conditions found in the sun's core. This means generating temperatures of tens of millions of degrees Celsius and confining the plasma long enough for fusion reactions to occur. One of the biggest challenges in fusion research is containing the plasma. Because it's incredibly hot, plasma tends to expand rapidly. To prevent it from touching the reactor walls, which would cause it to cool down and lose energy, scientists use powerful magnetic fields to confine the plasma. This is similar to how Earth's magnetic field traps charged particles in radiation belts. Several approaches to magnetic confinement have been explored, including tokamaks and stellarators. Tokamaks, like the famous ITER project, use a combination of toroidal, donut-shaped, and poloidal magnetic fields to create a complex magnetic cage for the plasma. Stellarators, while more complex to build, offer the potential for steady-state operation, unlike tokamaks, which operate in pulses. While significant challenges remain, the pursuit of fusion energy is a global priority. If successful, fusion could transform our energy landscape, providing a sustainable and abundant power source for generations to come. It's a complex and ambitious undertaking, but the potential rewards are immense. The challenge of achieving fusion. Achieving fusion energy on Earth is a monumental challenge, but the potential rewards are immense. Compared to nuclear fission, the process used in traditional nuclear power plants, fusion packs a much bigger energy punch. It generates 4 times more energy per kilogram of fuel. This staggering energy density is a primary reason why scientists worldwide are racing to turn fusion from a theoretical concept into a practical reality. So, what can we expect from the promise of fusion energy? A lot, actually. Imagine a power source millions of times more potent than burning fossil fuels. That's the promise of fusion. Most fusion reactors in development today use a combination of tritium and deuterium, specialized forms of hydrogen. The energy potential of these fuels is astonishing. Just a few grams could power a developed nation for years. What's even more exciting is the abundance of fusion fuel. Tritium can be produced by combining fusion-generated neutrons with lithium, a widely available element. Deuterium is readily extracted from seawater. These fuel sources are virtually inexhaustible, ensuring a sustainable energy supply for millennia. Unlike traditional nuclear power, which produces long-lasting radioactive waste, fusion generates minimal waste. This environmental benefit is a significant advantage of fusion energy. Future fusion reactors are being designed with safety as a paramount concern. Unlike fission reactors, which rely on complex control systems to prevent meltdowns, fusion reactions are inherently self-limiting. If conditions become unstable, the fusion process simply stops, and the plasma fuel disperses harmlessly. This inherent safety makes fusion a promising candidate for a clean and secure energy source. Furthermore, fusion reactions occur rapidly, preventing the buildup of harmful byproducts. The risk of a runaway reaction, a nightmare scenario in fission reactors, is virtually non-existent in fusion. While the challenges of initiating and sustaining fusion are formidable, the potential benefits for the environment and human society are immense. Fusion energy offers the hope of a low-carbon future powered by a virtually limitless, clean, and safe energy source. Replicating the Sun's core on Earth is a monumental scientific and engineering challenge. While gravity compresses the Sun's matter to initiate fusion, terrestrial scientists must create these extreme conditions artificially. To induce fusion reactions using deuterium and tritium, temperatures exceeding 100 million degrees Celsius are required. This is far hotter than the Sun's surface. However, temperature alone is insufficient. Precise control over magnetic fields and pressure is essential. Maintaining plasma stability within these demanding conditions is crucial for sustained energy production. Current experimental reactors are making significant progress towards achieving these stringent requirements. However, substantial obstacles, such as improving energy confinement and controlling plasma instabilities, persist. Overcoming these challenges is pivotal for developing practical fusion power. Engineering and material science challenges. Constructing a fusion reactor capable of withstanding and controlling such extreme conditions is an engineering marvel in itself. Developing materials that can endure these intense temperatures and pressures without melting or degrading is a formidable task. Additionally, the complex interplay between magnetic fields, plasma behavior, and reactor components necessitates sophisticated control systems and real-time diagnostics. Furthermore, the energy required to initiate and sustain fusion reactions is substantial. Efficient energy delivery systems and energy recovery technologies are essential for optimizing the overall energy output of a fusion power plant. The quest for fusion energy has united scientists and engineers from around the world. International collaborations, such as the ITER project, pool resources and expertise to tackle the immense challenges associated with fusion research. A diverse range of approaches, including tokamaks, stellarators, and inertial confinement fusion, are being explored to find the most promising path to commercial fusion power. Recent advancements in materials science, supercomputing, and plasma physics have accelerated progress in fusion research. The achievement of net energy gain in a fusion experiment marks a significant milestone, demonstrating the feasibility of harnessing fusion energy. However, scaling up fusion reactors to commercial power plant levels will require continued innovation and breakthroughs. The potential benefits of successful fusion energy are immense. A virtually inexhaustible, clean, and safe energy source could revolutionize global energy systems. Fusion power could significantly reduce greenhouse gas emissions, mitigate climate change, and provide energy security for nations worldwide. While challenges persist, the long-term vision of a fusion-powered future is inspiring. Continued investment in research and development is essential to overcome the remaining obstacles and unlock the full potential of fusion energy. Overcoming challenges in the pursuit of fusion. The journey to realizing fusion as a practical energy source has been marked by significant challenges. The JT60SA reactor, a cornerstone in this pursuit, epitomizes the complexities involved. Undertaken as a classified project in the mid-1980s, this ambitious endeavor required a complete rebuild from scratch. Despite being considerably smaller than the ITR project, the JT60SA is a formidable machine capable of containing 135 cubic meters of plasma. Data generated from its operations is invaluable to the broader fusion community, including the ITER project. Development of the JT60SA was a protracted process, significantly exceeding initial timelines. A myriad of challenges, from supply chain disruptions to the need for seismic upgrades following the devastating 2011 Tohoku earthquake, contributed to the extended project duration. The complex engineering involved in constructing and operating such a massive machine inevitably led to unforeseen setbacks. A critical incident involving a short circuit and subsequent helium leak in a superconducting magnetic coil highlighted the inherent risks and challenges associated with fusion research. Beyond the technical hurdles, the human element is integral to the success of fusion projects. The dedication and resilience of the teams involved are essential in overcoming setbacks and maintaining project momentum. The near disaster involving the cooling system leak underscores the high-stakes nature of fusion research and the unwavering commitment of the scientists and engineers involved. The JT60SA project serves as a testament to the complexity and perseverance required to advance fusion technology. While challenges abound, the potential rewards of successful fusion energy are immense. A clean, safe, and virtually limitless energy source could revolutionize human society and address pressing global challenges, the broader fusion landscape. The JT60SA is one piece of a global puzzle. Numerous countries and institutions are engaged in fusion research, exploring various approaches and technologies. The collaborative nature of this field is essential for sharing knowledge, overcoming challenges, and accelerating progress. As research progresses, it is becoming increasingly clear that fusion is not solely a scientific endeavor, but also a significant engineering and economic challenge. Developing cost-effective and scalable fusion reactors will require innovative solutions and substantial investments. Despite the complexities and setbacks, the pursuit of fusion energy remains a compelling goal. The potential benefits for humanity are too substantial to ignore. With continued dedication, international cooperation, and technological advancements, the dream of harnessing fusion power may one day become a reality. A near-catastrophic incident involving electrical insulation necessitated a prolonged repair process, underscoring the inherent risks associated with large-scale experimental facilities. To mitigate future occurrences, rigorous testing protocols for reactor components have been implemented. But the challenges aren't limited to engineering and safety concerns. The decision to exclude tritium from the JT60SA experiment simplifies certain aspects of the reactor's operation, but it comes with its own set of implications. Tritium, a heavy isotope of hydrogen, is a crucial ingredient for achieving efficient fusion reactions. Without it, the reactor can't fully replicate the conditions found in stars, where fusion naturally occurs. The significance of tritium in fusion research cannot be overstated. As a powerful energy source with unique properties, tritium is essential for generating electricity through fusion. The ITER project, with its planned integration of tritium by 2035, represents a major step forward in harnessing this vital element. Tritium's role is indispensable, not just for its energy potential, but also for its ability to make fusion reactions more efficient and practical. Japan has set its sights on achieving commercial fusion power by 2050 through the DEMO project, underscoring the nation's commitment to leadership in this field. Transitioning from experimental reactors to a power plant capable of producing net electricity is no small feat. Successfully managing the tritium fuel cycle, ensuring plasma stability, and developing advanced materials capable of withstanding extreme conditions are key challenges that must be addressed. Despite being smaller in scale than ITER, the JT60SA reactor plays a crucial role in developing the technologies required for demo and future fusion power plants. By operating as a testbed for advanced materials, magnetic confinement systems, and plasma diagnostics, JT60SA significantly contributes to the overall advancement of fusion research. The path to commercial fusion power is a complex interplay of scientific discovery, engineering innovation, and international collaboration. While challenges persist, the potential benefits of this groundbreaking technology are immense. A future powered by fusion offers the promise of clean, abundant, and sustainable energy, addressing some of the world's most pressing challenges. In the grand scheme of things, JT60SA is more than just a research facility. It's a symbol of hope and progress. The near-catastrophic incident and the decision to exclude tritium highlight the difficulties and complexities involved in this field. However, they also demonstrate the resilience and adaptability of the fusion research community. As JT60SA continues to serve as a critical testing ground, it helps pave the way for the technologies that will make future fusion power plants a reality. The insights gained here feed directly into larger projects like ITER, ensuring that each step forward is informed by rigorous experimentation and collaboration. The journey towards harnessing fusion energy is marked by both triumphs and tribulations. Yet every challenge faced and overcome brings us one step closer to realizing a world powered by fusion energy. The collaborative spirit among countries underscores the importance of working together to tackle global challenges and find innovative solutions. Beyond experimental reactors, Japan's comprehensive approach to fusion energy extends far beyond the confines of experimental reactors. The nation has embarked on a strategic initiative, the Fusion Energy Innovation Strategy, to solidify its position as a global leader in this transformative field. By fostering a robust domestic fusion industry and actively engaging in international collaborations, Japan aims to accelerate the development and commercialization of fusion power. The ITER project serves as a cornerstone of Japan's fusion strategy. Through active participation and collaboration with international partners, Japan seeks to acquire the knowledge, skills, and technological capabilities necessary to build and operate future fusion power plants. Strategic partnerships with European nations, solidified through agreements like the Broader Approach, are instrumental in achieving this goal. These collaborations facilitate the exchange of expertise, technology transfer, and joint research projects, creating a synergistic environment for innovation. Beyond international cooperation, Japan is investing heavily in domestic research and development. By nurturing a strong foundation of scientific and engineering talent, the country is building the capacity to overcome the formidable challenges associated with fusion energy. Balancing fundamental research with applied technology development is a key aspect of Japan's strategy. This approach aims to create a robust ecosystem that supports innovation at every stage of the fusion value chain. The growing interest and investment from the private sector have injected new vitality into the fusion field. This surge of private sector activity underscores the recognition of fusion energy as a potentially disruptive technology with immense commercial potential. Japan's strategy includes fostering a supportive environment for startups and entrepreneurs, encouraging them to develop innovative solutions to the challenges facing fusion energy. By combining government leadership, industry engagement, and international collaboration, Japan is positioning itself as a front-runner in the global race to commercialize fusion power. The ultimate goal is to develop a clean, safe, and virtually inexhaustible energy source that can address the world's energy and climate challenges. Building on fusion foundations, fusion research is a testament to human ingenuity and perseverance. The field is characterized by continuous evolution, with each advancement paving the way for the next. Before the ambitious JT60SA project, the JET facility achieved a groundbreaking milestone. In December 2023, JET concluded its experimental phase with a world record for energy output from a fusion reactor, generating a staggering 69 megajoules of energy in a mere 5.2 seconds, equivalent to powering 12,000 homes. This achievement underscored the rapid progress in harnessing fusion energy on Earth. Ambrogio Fasoli, a leading figure in the field, emphasized the profound implications of JET's success. This achievement signifies a growing mastery of fusion reactions, laying a solid foundation for future advancements. Recognizing the importance of cultivating the next generation of fusion scientists, Eurofusion and F4E have initiated programs focused on education and training. However, the field faces challenges in attracting young talent due to the perception of slow progress and lingering associations with nuclear fission. To address this, a sustained commitment to research infrastructure, education, and training is essential. The synergy between public and private sectors is crucial for accelerating the commercialization of fusion energy. Ilyana Ivanova, the European Commissioner for Innovation, Research, Culture, Education and Youth, emphasized the importance of bridging the gap between laboratory research and industrial application. This lab-to-fab transition requires a seamless integration of the public sector's long-term vision with the private sector's entrepreneurial spirit and industrial capabilities. Beyond the scientific and technological challenges, the economic and societal implications of fusion energy are profound. A successful fusion reactor could revolutionize energy production, providing a clean, safe, and virtually inexhaustible power source. Such a breakthrough would have far-reaching consequences for global economies, geopolitical relations, and environmental sustainability. To realize the full potential of fusion energy, continued investment in research, development, and infrastructure is imperative. International collaboration, knowledge sharing, and talent exchange are also essential for overcoming the complex challenges that lie ahead. By fostering a global community of fusion researchers and innovators, we can accelerate progress towards a future powered by this transformative technology. As JT60SA moves into its operational phase, it will play a critical role in advancing our understanding of fusion energy. The data and insights gained from this facility will contribute to the development of future fusion reactors, paving the way for a sustainable energy future. The collaboration between Europe and Japan on this project serves as a model for international partnerships in scientific research, showing that by working together, we can achieve great things. In summary, the unveiling of JT60SA at COP28 is a significant moment in the journey towards fusion energy. It highlights the importance of international collaboration in tackling global challenges and underscores the potential of fusion as a safe, efficient, and environmentally friendly energy source. The world will be watching as JT60SA continues to push the boundaries of what is possible in fusion research, bringing us closer to a future powered by the energy of the stars. What are the potential downsides of fusion energy? Share your views. If you enjoyed this text, don't forget to leave your thoughts in the comments and subscribe for more. Also, if you enjoyed this, make sure to check out the other videos you see on your screen.